The second example that we're going to do is a little strange, but it's also brilliant at the same time. So it's another vector projection problem. It says let C and D be the points defined by the vectors C equals minus I plus j, and vector D is I minus 2j. We're going to begin the problem with a rough sketch just to check the accuracy of our answers. We can see that vector C will be 1 unit to the left and 1 unit up, while vector D will be 1 unit to the right and 2 units down. Now, this already looks a little different to usual because it says we have to find the vector resolute of C parallel to D. So we need to find a vector U that is along D that ends directly in line with the end of vector C. Now, as we can see here, there's not really any part of D right now that ends up near that endpoint of vector C. So we're actually going to have to elongate D in the opposite direction. If I draw in negative D into the diagram, it will look something like this. This is great. I can see that negative D extends so it gets pretty close to the end point of C. So U will be that vector. It will just stop right in line with point C. That U will be our vector resolute. We also have W, the component of C that is perpendicular with vector U. I'm going to draw it in a little bit more detail, but just as messy. Remember the direction of your arrows? U goes to the point underneath C, and then W goes from the endpoint of U up to that endpoint of C. Now, in this case, U is in the opposite direction of D. It is still a scalar multiple of D, so gamma D, but it will just be in the negative direction of D. This will affect our scalar resolute in part B of this question. We still know that W, in this case, be careful of the vector letters they give you. So W will still be minus U, but this time plus vector C. Again, you can rewrite this as C minus gamma D. Once you have all the information in the diagram, we can find the vector resolute by using the same method as usual. We've got to start by finding gamma. Begin by saying that vector D, our original vector, dotted with W, our perpendicular vector, equals 0. Substitute that W equals C minus gamma D into the equation and rearrange for gamma. In this case, we'll get D dot C over D dot D, which is just the length of D squared, is equal to gamma. Always show these steps in your working out. D dotted with C, D is I minus 2j, C is minus I plus j. When we dot these together, we get 1 times minus 1 plus minus 2 times 1. We also know the length of D is equal to the square root of I component is 1 squared plus my j component was negative 2 squared. The length of D squared will be the square root of 5 all squared, so the length of D squared is just 5. If I expand my dot product, I'm going to get minus 1 minus 2, which is minus 3. So my scalar, or gamma, is minus 3 over 5. We can verify this with our diagram. Then we can find our vector resolute, U. So U is equal to minus 3/5 times vector D, which is I minus 2j. If you expand you'll get minus 3/5 I plus 6/5 j. The second part of the question says find the scalar resolute of C parallel to D. That just means find the directed distance of U. Now, because U is in the opposite direction to D, we know our scalar resolute will be a negative times simply the length of U. Therefore, our scalar resolute is minus times the length of U, where we can find the length of U, that will be the square root of minus 3/5 squared plus 6/5 squared. When we simplify that square root, the scalar resolute is equal to minus the square root of 45 on 5. And although in an exam you would keep it in exact form, I just wanted to approximate this to minus 1.34 so I can verify that the length and direction makes sense with our diagram. And it does. The length of U seems to be just over 1 unit long. And again, it's negative. That makes sense because it's in the opposite direction of D. For part C, we need to find a unit vector that is perpendicular to D. We already know a vector that is perpendicular to D, and that vector is vector W. So all we have to do is find the unit vector of W. We just say that W hat, or our unit vector, is equal to 1 over the length of W times the vector W itself. First, find vector W. Recall that W equals C minus vector U. C was minus I plus j, and U was minus 3/5 I plus 6/5 j. If I subtract U from C, we will end up with minus 2/5 I minus 1/5 j. Again, that looks realistic. If we look at W in our diagram, it looks like it goes to the left and down slightly. Now we can find the length of W. The length of W ends up to be the square root of 1 over 5 or 1 over root 5. And if you want to rationalize the denominator here, you get root 5 over 5. Therefore, W hat will be 1 over root 5 on 5 times the vector W that we found. When you tidy up the fraction here, 1 over root 5 over 5, you'll end up with just root 5. There we go. W hat is equal to root 5 times minus 2/5 I minus 1/5. So now you know vector projections. Have a go at the exercises. And in the wise words of Oprah Winfrey, do what you have to do until you can do what you want to do. And I know you only have 1 year left until you can do exactly what you want to do.